Welcome to this presentation on calcite precipitation events, understanding its drivers and implications. This is an experimental work that was conducted in 4 different lakes, 1 reservoir in Spain and 3 lakes in Estonia. You have here some pictures of these beautiful places. Most lakes and reservoirs are supersaturated in carbon dioxide, CO2. And these CO2 emissions from lakes have widely been attributed to net heterotrophy, where we consider organic sources as the main source of CO2. And dissolved organic carbon is used as the key variable for explaining CO2 emissions. You have here some key articles describe this topic, where lake metabolism and heterotrophy are used as the key parameters explaining CO2 emissions. But many recent studies report a lack of dependency in the relationship between organic carbon and CO2 supersaturation. This shows that we need to consider inorganic sources of carbon, such as calcite precipitation in lake models and carbon budgets. You have here again some key articles. They emphasize the role of dissolved inorganic carbon in carbon fluxes, and they also suggest that lake metabolism alone is often insufficient for estimating carbon budgets. Pelagic calcite precipitation is a relevant component of the global carbon cycle in lakes. Recently, we did an estimation of the global rates of calcification in lakes, and we see here to the left in the plot that these global calcification rates are not so much below those of the global organic carbon burial lakes rates. So they are very comparable in magnitude to global rates of organic carbon burial in lakes. And pelagic calcite precipitation is considered a long-term DIC sink and a short-term CO2 source, because according to its chemical equilibria, which you can see here, for 1 mole of calcite that precipitates, you have 1 mole of carbon, which is stocked in the form of calcite, and you also have 1 mole of carbon, which is released in the form of CO2. Calcification events can reach very strong intensities in summer, where it is not uncommon to find lakes in this condition here, where the waters take this milky appearance. These are called whiting events. And such events can have strong impacts on the carbon budget of a lake. So what do we know about calcification, its occurrence, and its conditions for its occurrence? Calcification usually follows a seasonal variation where it peaks in summer because primary production increases the pH, which leads to carbonate saturation. Also in summer, you have more phycoplankton and cyanobacteria, which offer ideal nucleation sites for calcification. And you have here a picture that illustrates this. Calcite forms usually around these organisms, which results in this cheese-looking like compound. Also, there are important physical-chemical conditions such as alkalinity, where a threshold of 1 milliequivalents per liter has been identified, under which calcification is unlikely to occur. Also, calcite saturation index is an important variable, and it usually peaks together with pH during the summer season. But there's still a lot of uncertainty because there's a lack of a mechanistic understanding of its occurrence, and therefore there exists no reliable parameter for calcification that could be used to account for this process in lake models and carbon budgets. So the objectives of this work is to understand what are the mechanisms that control pelagic calcite precipitation. Our hypothesis for primary production is that we expect a positive effect of net ecosystem production on calcification. And as for physicochemical conditions, we expect a positive effect of alkalinity and calcite saturation on calcification. Here's the experimental setup for the in situ incubations that we performed in this work. So what we did, we collected surface water from the deepest area of a lake. Then we measured the initial conditions of temperature, oxygen, pH, alkalinity, and calcium. Then we incubated transparent bottles for the normal conditions of production, and we incubated dark opaque bottles for the conditions without production to measure respiration. We incubated these bottles for 5 to 6 hours at the lake shore. They were submerged in the water. And then we measured the final values of temperature, oxygen, pH, alkalinity, and calcium. We did this experiment in one reservoir in Spain, where we did 5 campaigns. This is the Sau reservoir. And then next year we did the same experiment in 3 lakes in Estonia, where we conducted 2 campaigns in each lake. And you can see that we cover with these 4 lakes a wide range of alkalinity. We also had a high frequency measurement station in Sau reservoir, which was measuring automatically every 5 minutes from May to October 2018. It was measuring oxygen, pH, temperature, conductivity, and CO2. We also did surface water sampling in Sau reservoir regularly around every 2 weeks, where we were measuring calcium, alkalinity, oxygen, pH, and temperature. So here are the results. First step is to identify the cases of potential calcification. So in these plots, each bar represents a campaign. So to the left, you have the calcite saturation index. You see all campaigns have a positive calcite saturation, except for Lake Valgutta-Musjerv, which is a bog lake, a brown water lake with low pH. And therefore, this is the lake we would least expect calcite saturation, calcite precipitation to occur. To the right, you have a plot that shows the changes in alkalinity. We used this as a proxy for calcification, where we assume that a decrease in alkalinity is caused by calcification. So here you see that there are 4 cases where calcification is clearly not occurring. And so for the next slides and the following analysis, we are only keeping the campaigns which show potential calcification. And these are 7 in number. Here we are looking at the effect of net ecosystem production on calcification. You see that there is no direct effect of NEP on calcification. However, if we consider the effect of NEP on calcification within the larger context of the calcite saturation index, then we see a strong logarithmic effect of calcite saturation on the ratio between calcification and net ecosystem production. This shows that the short-term effect of NEP on calcification depends on the longer-term effects of calcite saturation. So in our incubation bottles, we are observing changes of oxygen caused by NEP at an hourly scale. However, for calcite saturation, the water that is incubated is actually already carrying the legacy of the calcite saturation that actually follows a seasonal scale. So we have to consider the short-term effects of NEP and the long-term effects of calcification to see how they regulate or they drive calcite saturation. This is maybe more clear in this plot, This shows a calcification event that occurred in Sau Reservoir. So from top to bottom, you have the time series, high frequency measurements of temperature, then of oxygen, then sampling water, surface water sampling of calcite saturation and of calcium concentrations. So what we see here is a calcification event that occurred during this period. This is shown by this clear decrease in calcium, which is caused by calcification. Now, why did this happen here? We see that there was a clear increase of temperature, which resulted in a peak of oxygen saturation, a peak of production, a peak of NEP. At the same time, we're having a peak of calcite saturation. So all the conditions are met for calcification to occur. Now, if we look right after this calcification event, we see that calcification seems to be halted. There is no more any decrease of calcium during this period. And this is despite having still very high saturation of oxygen, so high production. So why are we not observing any calcification? Well, most likely because the calcite saturation in the meantime has diminished quite substantially. And so despite having strong production, we are no more having a very high calcite saturation, which is preventing calcite precipitation to occur. In such calcification events can have strong impacts on the response of dissolved inorganic carbon to metabolism. On this plot, you have on the x-axis the ratio between calcification and NEP. And on the y-axis, you have the ratio between changes in DIC and changes in oxygen. So you see that when the calcification is almost zero, you see that the ratio between DIC and DO follows this typical one-to-one metabolic stoichiometry, which is expected from metabolism. That means an increase of 1 mole of oxygen would result in a decrease of 1 mole of DIC and vice versa. However, when at higher ratio between calcification and NEP, that means that for 1 mole of NEP you would have more calcification occurring. In such cases, you can see a strong deviation from the one-to-one metabolic stoichiometry. Instead of being a ratio of -1, we are having here a ratio of -8. So the effect of NEP on calcification can be strongly potentiated at high calcite saturation, and this can then result in large imbalances in the response of DIC to metabolism. And such imbalances caused by calcification are not accounted in lake models. So the implications and conclusions of this work is that the occurrence of calcification is simultaneously governed by short-term effects of NEP and longer-term effects of calcite saturation. The calcification to NEP ratio is strongly potentiated at higher calcite saturation, potentially resulting in intense calcification events or whiting events. So it is really when the lake meets this momentum where you have a peak of production and a peak of the calcite saturation index, that's when you can expect calcification to occur at higher rates. Calcification causes deviations from the metabolic one-to-one stoichiometry between oxygen and DIC, and therefore it is important to account for these deviations in lake models. And our results suggest that yes, it is possible to parameterize calcification using NEP and calcite saturation simultaneously. And this way, we would be able to account for calcification in lake models and carbon budgets. Thank you for your attention.